Alrighty, guys. So, quick revision of vectors. So, let me share. There we go. So, remember. So, remember, vectors are generally written vertically. They can be written horizontally, but they're generally written vertically. And two-dimensional vectors have two components. Three-dimensional vectors have three components. Importantly, the definition of a vector is that it's a quantity with magnitude and direction. Now, because it specifically has direction, your symbol is the arrow above it showing the direction. So A and B would be 2 points, the start point and the end point. And you know which one is the start point because that's where you have just the little end of the arrow, and the end point is where the head of the arrow is. So this is a vector going from A to B. This is a vector going from B to A. Now, in a textbook, you'll see vectors written in bold. We don't write in bold. So to denote a vector, if it's not given with a start and end point, we just underline it. So if it's got 2 points, we put the arrow. But if it's just a letter denomination, we underline it. All right. And then we had a look at it last time that you have vectors, and the way that we name vectors is kind of by almost looking like their gradients, where you look at their run, you look at their rise, you always put your X, then your Y, from start to finish. So this one here, this was a run of 2 in the positive direction, a rise of 1 in the positive direction, therefore the vector was 2, 1. And irrespective of where the vector was, that is what happens. That vector will be the same vector wherever it is on the Cartesian plane. So if we get the direction to be in the opposite direction, all that happens is that my vector becomes negative. So both coordinates become the negative values of what they were. If one of them was a negative, it then becomes a positive. So your signs will swap. All right. Now, if we have a vector, and let me whiteboard this. Buddy, I am very glad that you managed to work so hard and get it all right. All right. So if we have a vector, and this vector is, say, 3, 4, and I say to you, what is the length of this vector? Well, let's have a quick drawing of it. Y, X. Now, we need to draw 3, 4. So we need to remember that we're going to run 3 and rise 4. So let me change my color blue. So we run 1, 2, 3, and then we rise 4. 1, 2, 3, 4. There we go. So there's my end point. There's my starting point. And I'll use green as a straight line. There is my vector. Now I need to calculate the length of this vector. And how do I do that? Well, hopefully we can notice that there is our old friend, the right angle triangle. So we can most definitely use Pythagoras, or the Pythagorean theorem, if you want to be Lani, to calculate this. Because we know this length is 3. We know this length is 4. So you can either do your normal Pythagoras, calculate it, or you can know that this 3, 4 is a special kind of triangle. It is known is a Pythagorean triple. So if I see a 3 and a 4 on the legs, I will always know that my hypotenuse is 5. I'm really hoping I don't need to show anyone Pythagoras. However, if you do need it, that is part of the lesson, and I will be willing to show you. So this is a 3, 4, 5 triangle, which means that if you have a leg of 6 and 8, you can automatically know that the hypotenuse is going to be 10. Sure, Stefan, you are busy. If I have legs of 9 and 12, I will know automatically that my hypotenuse is 15 because I'm taking this and timesing by 2, or I'm taking this and timesing by 3. This relationship will always hold. And there are a couple of Pythagorean triples that are very useful. 2 of them more particularly. You have a 3, 4, 5, and then you also will have a 5, 12, 13 triangle. All right. And it is literally that simple to calculate the length. So if you're given a vector xy, to calculate the length of my vector, it is simply Pythagoras, being the square root of the one side squared plus the other side squared. But just like in all maths, we have notation for this. All right, so if this is, for example, vector A, the length of A is shown by almost absolute value signs, the 2 vertical lines. In formal maths, this is known as also the modulus of A. All right, so calculating length, very simple. There's no problem with that. If we want to add vectors, it's also incredibly simple. You have 2, 3, and you have -1, 4. Just like with matrices, you do it component by component. So 2 plus -1 is 1, because remember, a plus and a minus together make a minus. And 3 plus 4 is 7. Yay! Very complicated. You guys can see, like, how are we going to remember to do this? All right. Similarly, if we want to do subtraction, let me use the same example because that is just what I do. We're gonna, and now my heading must also change. How do we subtract vectors? We subtract them component by component. 2 minus -1, a minus and a minus make a plus. So 2 plus 1 gives me 3. And 3 minus 4 gives me -1. Amazing. All right, so now nothing of great change or significance in the sense of something being different. Everything is totally the same. We also have our scalar multiple. So if we have our vector 2, 3, and we want to multiply this by the number 4, just like with matrices where you multiplied it to every component, in vectors you multiply it to every component. It is 4 times 2 and 4 times 3, which comes out at 8 and 12. What does the scalar multiple do? It just makes my vector longer, but it keeps the same direction. So instead of having a vector of 2, 3, change colors. So instead of having it at that length for this vector, it would now be, we add another 1, we add another 2, we add another 3. Okay, cool. That is now this vector. So it is longer, but same direction. All right. Nothing too big, nothing too complicated. All the stuff that we've seen before. So all of this is fun and fine. If we have a look at a past paper question, for example, it says, buddy, I struggle to believe that. Calculate the following. And this is for a whole mark on the paper. Luckily, that's not too difficult. 3 plus 1 gives me 4. And minus 2 plus minus 1. Plus and a minus makes a minus. Minus 2 minus 1 gives me minus 3. 1 mark. A whole mark in the bag. So, buddy, if you get a 16-year sane and a 17-year insane, that means you're quite old. Next one is this. What I'm going to do is I'm going to share this one with you rather. You have A, you have B. It says points A and B are marked on the grid. You have vector BC, which is minus 4, 0. So vector BC, we need to remember, starts at B, ends at C. It doesn't start at 0. So we need to go to B. And remember, this is always X and Y. So my X is moving 4 in the negative direction, which means to the left. 1, 2, 3, 4, and 0 down, meaning that that is going to be my point. That is C. That is my vector BC. So plot point C, there's point C. I've drawn in the vector. You don't need to do that, but I'm trying to show you stuff. Now we need to write AC as a column vector. Now again, please note, I'm sure a lot of you are thinking that's fine. 1, 2, 3, 1. Okay, great. So it's 3 up, 1 to the left. There we go. 2 things that are wrong with that. First thing that's wrong with it, you'll always do your horizontal first, then your vertical. So it's 1 that we're moving horizontally and 3 that we're moving vertically. Second problem, it is not the vector CA, it is the vector AC. C. That's a problem. So A to C means we move 1 to the right and then 3 down. So the vector AC is going to be 1 minus 3. Not 3 minus 1, not minus 1, 3, 1 minus 3. All right, this sort of thing is very important because understanding direction of vectors is important for when you actually get to your proper extended syllabus questions. These two questions, let me get rid of that. Nice. All right. These two questions have actually been on a core paper, not an extended paper. So if I bring out an extended paper, we can get a question that looks like this. So this looks quite a lot more interesting, doesn't it? And you might be saying scary, but I'm saying interesting. So we have this regular hexagon. Is that line over BC always pointing right? So in notation, it's always best to get it to point right, but equivalently, you could write it as CB with it pointing left. That is still acceptable. It would be an equivalent form. All right. So O is the origin, and this is my regular hexagon. I've been told that OP is my X and OT is my Y. I'm underlining it because I'm not going to be able to write in bold. We need to write down in terms of X and Y, or in its simplest form, this, QR. So QR, we need that vector over there. Now we need to remember this is a regular hexagon. And a regular hexagon means that all interior angles are the same and all side lengths are equal. This side, QR, and this side, OT, are equal, which means that it is simply Y. Great, because we can take this, move it all the way down, and this would line up perfectly with that in the same direction. So yes, SR would equal X as well. That over there, that would equal X as well, 100% correct. So we are now looking for PQ. So that one over there, I'm going to change color. So we're looking for that vector over there. Well, that's a little bit more complicated because we don't have something in that direction. But can we make up something to get to that direction? Well, if we start at O, because we generally try and start at O, we can go in this direction, that's X. If we put another vector here, and let me get a better color. So I'm going to put another vector there that is X. So it's the same length in the same direction. And then I put another vector up this way that is Y. I can do that because I know that that forms a parallelogram. So I very much can add on that, and it will meet at Q. So if I want now PQ, to start at P, I can go there to my new point, and then there, and get to Q, which means that this is actually X plus Y. And answers can be written as the sum of vectors, and most likely will be written as the sum of vectors. The position vector of S. Position vector, very important. That means that it starts at the origin. How did we know we were going to be doing that? Because you've seen questions like this, and you can then put that method into your toolbox of methods. You can move these vectors to anywhere, and that's why we could do this. So I just took this and I moved it further. I took this, I moved it further, because I need to try and start it there, end there, but using these two directions to do it. If I wanted to, I could have gone up first and then across. That's fine. It's then y plus x, which is exactly the same. So position vector of S means I have to start at 0, get to S. So this is a very similar scenario. I can get to y. I've got my y there. 0 to t, that's not a problem. But now, how am I going to actually get my vector? So I want the vector OS. So from O, I can get to T. Can I get from T to S? Well, now that I've worked out PQ, I know what this is going to be. TS is actually the same as PQ. We can see that and that are the same. So therefore, we do exactly the same method. I change my color to what I wanted. There we go. So it's going to be y plus x plus y, which is therefore x plus 2y. If you didn't see that that and that were the same, you could just as easily have taken y, drawn another y up there, and then drawn another x over there, and then you go y plus x, 2y plus x. So the big trick with vectors is you've got to use the directions given to you, even if you add in other vectors, and it's only using the direction given to you from the starting where you're looking at to the end, going along a path. You'll almost never be able to just go there. I mean, the fact that they asked for QR, so QR, which was that, which is the same thing, that was your giveaway question. All right, so we are going to continue with this in our next lesson, and then we can do a couple more questions, because generally this kind of thing really, really messes people up. All right, and ironically, this is not a square, this is still a parallelogram, because we're not given that x and y are equal. So yes, it is 2 x's and 2 y's, but because x and y are not equal, we don't know.